For over a century, the most studied prehistoric monument on Earth has been examined by archaeologists, astronomers, geologists, historians, and engineers who have produced thousands of papers, dozens of competing theories, and no consensus on the questions that matter most. How was it built? Why was it built? What does the precise astronomical alignment of its stones actually mean in terms of the beliefs and knowledge of the people who placed them there 5,000 years ago? These questions have resisted every tool that science has brought to bear on them. And then a different kind of tool was pointed at Stonehenge. Not a trowel, not a spectrometer, not a ground-penetrating radar system. An artificial intelligence trained on the full breadth of human knowledge about Neolithic archaeology, astronomy, geology, engineering, and anthropology, given access to every published survey, every laser scan, every astronomical study, every geochemical analysis, and every piece of oral and documentary historical evidence ever produced about this site. And what the analysis returned was not a neat solution to the mystery. It was something more unsettling than that, a series of findings, each one individually explicable, that in combination point toward a level of knowledge, planning, and cosmological sophistication in the builders of Stonehenge that the accepted model of Neolithic Britain has never fully accounted for. Stonehenge stands on Salisbury Plain in Wiltshire, England, a landscape of rolling chalk downland that has been continuously inhabited and ceremonially used for longer than almost any other part of the British Isles. What is visible above ground today is the remnant of a structure that went through multiple phases of construction and modification, spanning more than 1,500 years, from approximately 3000 BCE when the first earthwork enclosure was dug, to around 1500 BCE when the last known modifications to the stone settings were made. The iconic image of Stonehenge, the massive sarsen sandstone trilithons arranged in a horseshoe and ringed by a circle of smaller uprights with lintels, represents only one phase of a monument whose full complexity extends both deeper into the ground and wider across the surrounding landscape than the standing stones alone suggest. The car parks, the visitor center, the road that was rerouted away from the monument in the 20th century all sit on a landscape riddled with buried features, ancient pits, post holes, cremation deposits, and processional avenues that together form a ritual complex of extraordinary scale whose full extent is still being mapped. The AI analysis that produced the findings now circulating in the archaeoastronomical and computational archaeology communities began not with Stonehenge in isolation, but with the full data set of everything known about it in context. High-resolution photogrammetric surveys of every surviving stone surface, the complete archive of excavation records stretching back to the earliest systematic digs of the 19th and 20th centuries, the results of recent geophysical surveys that have identified buried features in the surrounding landscape without excavation, isotopic and geochemical studies of the stones themselves that have traced the origin of the bluestones to the Preseli Hills in Wales, approximately 250 miles from Salisbury Plain, and the larger sarsen stones to Marlborough Downs, about 25 miles to the north. Archaeoastronomical analyses of the monument's alignment relative to the movements of the sun, moon, and stars, and the broader comparative database of Neolithic and Bronze Age monument traditions across Britain and Western Europe that provides the cultural context within which Stonehenge must ultimately be understood. What the AI was asked to do with this dataset was not simply to summarize what was already known. It was to look for patterns, relationships, and structural properties in the combined data that human analysts, working within the necessarily narrow focus of individual academic disciplines, might not have identified when examining their own portion of the evidence in isolation. The cross-disciplinary synthesis that an AI can perform at scale, identifying connections between geochemical data and astronomical alignment data and engineering analysis and landscape archaeology simultaneously, is qualitatively different from what any individual researcher or even a large collaborative team can accomplish when each member brings deep expertise in one domain and necessarily more limited engagement with the others. And it was in exactly this kind of cross-disciplinary synthesis that the most significant findings emerged. The first finding involved the precision of the monument's astronomical alignments, which turned out to be considerably more sophisticated than even the most detailed previous analyses had established. The alignment of Stonehenge's main axis with the midsummer sunrise and midwinter sunset has been documented since the late 19th century and is one of the best established facts about the monument. What the AI analysis revealed was that this alignment is not simply a general orientation toward the solstice sunrise direction. It encodes in the precise placement and geometry of the stones a level of astronomical accuracy that requires either long-term systematic observation of the sun's behavior across many years or the inheritance of accumulated astronomical knowledge from an older tradition that had already done that observational work. The axis of Stonehenge is aligned not to where the sun rises on the summer solstice in a general sense, but to where it rises on the specific horizon as seen from the center of the monument, accounting for the local topography, with a precision that deviates from the true astronomical bearing by less than 1 degree. Achieving that precision without modern instruments requires sustained, systematic, multi-generational observation. It cannot be arrived at by a single group of builders working from intuition or rough approximation, but the AI analysis went further than the solstice alignment, which was already known. It identified a secondary set of alignments encoded in the geometry of the stone arrangement that had not been previously recognized as a coherent system. The positions of specific stones within the Sarsen circle and the inner bluestone settings, when analyzed as a geometric network rather than as individual elements, encode alignments to significant lunar standstill positions, specific points on the horizon where the moon rises and sets at the extreme limits of its 18.6-year cycle. The lunar standstill cycle is one of the most complex and long-period astronomical phenomena observable with the naked eye. Recognizing it, understanding it well enough to predict where on the horizon the moon will appear at its most extreme northern and southern positions requires a minimum of about 40 years of continuous, systematic observation, because you need to watch at least 2 complete cycles before you can be confident you have identified the true extremes rather than near maximum positions. The encoding of lunar standstill alignments in the geometry of Stonehenge's stone placement implies that whoever designed the monument had access to astronomical records, spanning at minimum 2 generations, and more likely several. The second major finding from the AI analysis concerned the engineering of the monument, and specifically the question of how the lintels, the horizontal stones that rest on top of the sarsen uprights to form the characteristic trilithon and circle structures, were shaped and fitted. Each lintel is not simply a stone block placed on top of 2 uprights. It is shaped with a slight curve on its outer face to match the curve of the circle, so that the complete lintel ring forms a geometrically true circle rather than a polygon. And the connection between each lintel and its uprights is not simply a matter of gravity and balance. The lintels are locked to their uprights by mortise and tenon joints, circular projections on the top of each upright that fit into corresponding depressions carved into the underside of the lintel, a jointing technique borrowed directly from timber carpentry and translated into stone with a precision that required the builders to accurately predict, before any stone was raised, exactly where the mortise projections would end up relative to each other and to the tenon sockets that would need to receive them. The AI analysis of the engineering specifications of these joints, cross-referenced against experimental archaeology studies of how the stones could have been raised and placed using Neolithic technology, produced a finding that several engineering researchers who reviewed the output described as surprising. The tolerances achieved in the mortise and tenon joints at Stonehenge are tighter than the tolerances that would be necessary for the joints to function as structural connections. The joints work perfectly well at the precision actually achieved, but they would also have worked at substantially lower precision. The extra accuracy invested in the joints, accuracy that required additional labor with stone tools to achieve without providing any additional structural benefit, suggests that the precision was itself meaningful to the builders, that it was a feature rather than simply a byproduct of careful workmanship. What that meaning was, whether it reflects a ritual requirement for perfection in sacred construction, a demonstration of technical mastery as part of the monument's social function, or something else entirely, is not something the engineering analysis alone can answer. But the identification of intentional over-precision as a systematic feature of the construction, rather than a random variation in workmanship quality, is a genuine finding that changes how the engineering of the monument should be understood. The third and most difficult to categorize finding from the AI analysis involved the landscape surrounding Stonehenge rather than the monument itself, and it emerged from the synthesis of the geophysical survey data with the monument's geometry in a way that neither dataset had suggested when examined independently. The Stonehenge landscape is not simply the setting for a stone circle that could, in principle, have been built anywhere on Salisbury Plain. It is a carefully chosen location within a landscape that was already ritually significant before the first stones were raised, and the relationship between the monument's geometry and the natural features of the landscape it sits within turns out, under AI analysis, to be more deliberate and more precise than previous landscape archaeology studies had established. The avenue, the ceremonial approach road that leads from Stonehenge's northeast entrance toward the River Avon, approximately 3 kilometers away, was already known to align with the solstice axis of the monument. What the AI analysis revealed was that the avenue's alignment is not arbitrary in relation to the landscape it crosses. It follows, with remarkable fidelity, a natural ridge in the chalk geology of the area, a feature formed by periglacial processes during the last ice age, that runs in the same direction as the solstice alignment before the builders of the avenue arrived. The natural ridge, invisible to a casual observer but detectable in high-resolution topographic data, appears to have been recognized by the builders as a landscape feature that already pointed toward the midsummer sunrise, and the avenue was constructed to follow and formalize this natural alignment rather than to create an alignment from scratch. The site of Stonehenge was not chosen arbitrarily and then aligned with the sun. It appears to have been chosen specifically because the natural landscape at that location already embodied the alignment. The monument was built to make permanent and monumental what the earth itself had written in the chalk below. This finding, the recognition of a pre-existing natural alignment in the landscape, that the monument formalizes rather than creates, reframes the question of why Stonehenge is where it is in a way that has significant implications for how we understand Neolithic cosmology. The builders were not imposing their astronomical knowledge on an indifferent landscape. They were reading astronomical meaning in the landscape itself, identifying places where the natural world had already encoded the patterns they considered sacred, and building in those places to make the meaning permanent. This is a qualitatively different relationship between humans and landscape than the conventional model of Neolithic monument building implies, and it suggests a tradition of landscape reading, of identifying places where natural features align with astronomically significant directions that may have been operating across the British Isles for generations before any stone was raised at Stonehenge. The question that all three of these findings converge on, the question that the AI analysis raises and cannot itself answer, is where the knowledge came from. The astronomical knowledge required to encode the solstice alignment with sub-degree precision, the lunar standstill alignments that required decades of systematic observation, the identification of the pre-existing natural alignment in the landscape, the engineering precision that exceeded structural necessity. All of it implies the existence, in Neolithic Britain, of a tradition of knowledge that was systematic, accumulated across generations, carefully preserved and transmitted, and sophisticated enough in its astronomical and geometric components to design and build one of the most precisely constructed monuments in the ancient world. That tradition left almost no other direct physical record. There are no texts, no schools, no documented transmission mechanisms that archaeology has identified. The knowledge existed, was applied at Stonehenge, and then largely disappeared from the archaeological record. Some researchers who reviewed the AI findings pointed to the broader landscape of Neolithic monuments across Britain as evidence that Stonehenge was not an isolated achievement, but the culmination of a long tradition of monument building, astronomical alignment, and cosmological thinking that had been developing for centuries before Stonehenge's construction. The timber circles, the long barrows, the causewayed enclosures, and the earlier stone settings at sites across Britain all reflect a widespread tradition of astronomical awareness and monumental expression that Stonehenge brought to its highest known expression. But even in this broader context, the precision and sophistication of the Stonehenge alignments as revealed by the AI analysis stands out as qualitatively different from what the rest of the tradition had produced. What is hard to explain is not any single element of what the analysis found. Solstice alignments in prehistoric monuments are well documented globally. Lunar standstill awareness has been identified at other British sites. Careful stoneworking is a feature of many Neolithic structures. Each finding in isolation fits within the known repertoire of Neolithic achievement. What is hard to explain is the combination, the co-occurrence at one site of all of these sophisticated elements simultaneously, integrated into a single coherent design that encodes multiple layers of astronomical and geometric meaning, while also functioning as an engineering achievement of the highest order that Neolithic technology was capable of producing. The probability of all of these sophisticated elements appearing together by independent development, rather than as the product of a single coherent and highly developed knowledge tradition, is what the AI analysis identified as statistically unlikely in a way that human analysts examining the elements individually had not fully registered. That is what makes the findings hard to explain. Not that any one element defies explanation, but that the explanation required to account for all of them together implies a tradition of knowledge in Neolithic Britain that our current archaeological record has not fully captured, a tradition sophisticated enough to design Stonehenge, but leaving so few other traces of itself, that we are still reconstructing its existence from the monument it produced, rather than from direct evidence of the people who held it. The stones have been standing for 5,000 years. They have been studied by every method available to every generation of researchers who encountered them, and an artificial intelligence, given access to everything, those generations of researchers found and asked to look at all of it at once, found patterns in the combination that the individual pieces had concealed. The monument is the same. The data is the same. What changed was the scale and simultaneity of the attention brought to bear on it. And what that new kind of attention found in the oldest question in British archaeology is not a final answer. It is the clearest view yet of how much the question still contains.